Okay. So, that being the case, let us now delve into something new. Here comes the next important concept, which we already alluded to and even discussed a bit in terms of in one of our previous discussions. Okay. What is the whole idea here? Let us examine that. Recall that we had for the electric field E of t is a half square root of I of t. Square root of I of t is what we call the real amplitude. Okay. This was multiplied by exponent I omega naught t minus phi of t, and the left hand side is a real quantity, and we the rest of it, the first term is in the most general case complex. So, we have C c going together with the factor half. So, earlier on indeed in our discussions we had the question about, hey, what is phi of t, what is this doing here, and we also were wondering what is with the bias that we have for the carrier frequency omega naught. What is so great about omega naught that we are calling this the carrier frequency and giving it a special designation, right? And what about phi of t? What is hidden behind it? Why have we introduced this? Compare this with an even earlier description, where we essentially had a field description where E naught, let us say, was constant, exponent of I k dot r, where k and r are vectors. K is constant, the propagation vector for a plane wave. We had this, recall, multiplied by exponent of minus I omega naught t plus theta constant, and theta is a constant phase, constant value, which we call the absolute phase or the initial phase and whatever not. We even said, okay, this could be something not of great significance. Can we measure this? I mean, we can ask questions of that kind, right? Why not? But now in terms of drawing an analogy, theta and phi of t seem to belong to the same species. These are two phases which essentially tag along with the carrier frequency omega naught, and the piece omega naught t, which essentially primarily, recall that this piece omega naught t emerged out of the fact that we said that propagating waves are described by a mathematical function of the form x minus v t. So, this v t component, right, which is the key to propagation, essentially brought about this omega naught, because omega by k was the phase velocity for that, for a monochromatic wave, right. So, this is all arising out of propagation. So, this is essential, and the rest seems to be additional baggage, but this additional baggage is not really baggage, it is essentially something that here it may seem as a matter of completing the course by adding a constant next to a linear term in time, whereas here it seems to be something that we have deliberately introduced, which is to make this description as generalized as possible. But in an attempt with doing so, we have also done the following. Since phi of t, we do not know the form of phi of t. Do we know? We have to if we know, great, but if we do not know, in the most generalized scenario we probably do not know, we have to make attempts to measure it. As completely as possible and as far as is necessary. Okay. So, in which case if we do not know the details of this function, what we can do is we can then expand this by Taylor and say that we should essentially have we essentially need to expand this in a Taylor series and go further forwards, right. So, what this essentially did to us is that in its Taylor expansion, we now in the process of writing this down, we have introduced another term which is linear in T, correct. We have a term which is linear in T and we followed by a term that is quadratic in T. So, for now let us essentially focus only on the term which is linear in T. Okay. If I now consider the description of E of t up to this point, it is the square root of I of t exponent of I omega naught t minus phi at t naught some chosen time plus phi prime at t naught, prime denoting the derivative with respect to time, and t minus t naught plus higher order terms that closes my phase function and the complex conjugate. Without any loss in generality, I can set t naught to be 0. Okay. And for the sake of also maybe some oopsie, for the sake of some convenience too, let us remove at t is equal to 0 and keep this at t. So, then evidently we now have in this expression we should have all these as negative signs because of the way we had written it earlier, omega naught minus d phi. Okay, I should write my phi's consistently because there are too little phi's, that is also the challenge sometimes. Plus higher order terms in the phase function plus the overall complex conjugate of all the terms that precede this. Okay. Just check and tell me if I got the maths right by set where I considered t naught to be 0 without losing anything in general. It is just a shift of the time axis, right. Now, you see what has happened in the process of introducing this more general phi of t. We have this entire term mimicking the carrier frequency, or we have tampered with the carrier frequency of the pulse. Earlier I argued that the carrier frequency itself has a physical, has a robust physical meaning only if d phi by dt is smaller than omega naught. Otherwise, what is omega naught? omega naught is only a majority participant. Unless it is a majority participant in this, it probably has no reason to be given the special designation of a carrier frequency, right. So, as a consequence, in the process of generalizing this, we have given way, okay, for this phi of t function to creep even into the definition of this all important carrier frequency, which is what it seems is sort of carrying the wave through, because the envelope contains a lot of information, but the carrier is literally what carries it, right. That is again coming out from the propagation part, Vt x minus Vt. Okay. So, this is vital to the propagation of the wave, but then we have sort of tampered with it using the phi function. Of course, we did it knowing fully well what we intended to do. So, this temporal phase function phi of t is, if you wish, the culprit who makes life more challenging. But once you admit that into the game, you essentially we must admit to the concept of an instantaneous frequency, instantaneous angular or instantaneous cyclical frequency. Omega instantaneous of t or nu instantaneous of t, there is no escape, right. There can be no escape to this, and well, or that makes life more interesting and the physics richer, if anything. Okay. So, therefore, this is kind of easy to see. In other words, consider any a particular time t is equal to t, some instant of time, or we could have called this t naught. At that instant, okay, the total phase of the wave is omega naught t minus phi of t, without any approximations for phi in its full glory, the full Taylor expanded phi. But in this case, you should know phi to as many Taylor terms as necessary, or have some other analytical way to figure out what phi of t would have been. If either is the case, then you know this, and we can determine phi of t at any instant of time. Now, exactly one period later, okay, one wave period later, the period being the period as we knew, considering only the carrier frequency omega. Okay. One carrier period later, the total phase, okay, will be by its very definition being omega naught t minus phi, okay, it will increase to phi naught plus 2 pi. It should indeed increase by a factor 2 pi, and on the right hand side, let the time evolve by capital T. Okay. So, phi of t essentially is the secondary phase function, and as I said, for omega naught to have robust physical meaning, this variation in time must necessarily be slower. Okay. Now, let us take the two equations, right. Let us consider, let us call the top equation 1 and this equation 2. Subtract the two, so that on the left side, this is really elementary algebra, right, the factor of 2 pi remains, and on the right side we have omega naught times the period t minus phi of t plus t minus phi of t. Alright, are you with me? Now, if we divide the entire thing by the amount t, that is the period, we essentially get what the instantaneous frequency omega should be. Omega instantaneous should be, omega instantaneous is omega naught minus phi of t plus t minus phi of t, where the second t always is the period. Okay. But then the period of a wave for an optical petahertz wave is actually quite a small number in time in terms of absolute numbers. So, this derivative, we can therefore treat this finite difference phi of t plus t minus phi of t to be a derivative, and essentially we have given the coefficient of the first order term of the Taylor series a physical meaning, that is to say that it is an instantaneous frequency. In the domain of cyclical frequency, or just what we call frequencies, we essentially have this to be the same. So, this is nu naught minus 1 by 2 pi multiplying d phi by dt, because we use the angular frequency to describe phi of t. Okay. The instantaneous frequency as a consequence is a quantity of importance for what we call ultra short laser pulses. Okay. Pulses whose amplitude essentially is significant only over a reasonable number of optical cycles. It is not millions of optical cycles under a non-zero envelope. It is maybe tens, it is let us say tens of, or possibly even hundreds. Yeah. So, in such scenarios, the notion of an instantaneous frequency essentially has a lot of physical significance and meaning. So, enter instantaneous frequency in our books. Okay. Let us continue. Now, the next notion comes about from the following. Earlier, the notion of instantaneous frequency came about from the fact that the phase term that we had in our description of the simplest wave of consideration had minus omega naught t plus a theta. We generalized this theta. Instead of it being constant, we said let it vary slowly in time, slow compared to omega naught, all right. But then this simplistic ideal wave, where we had just a monochromatic scenario where we had just one frequency in the entire description and content of the wave, there we could define a certain velocity. Okay. Recall, we said that we have a wave, time domain, and t, and this is the amplitude axis. What we said is that a phase point, let us say the positive maximum of the field, has essentially propagated, gone forward in time at a given point, and likewise in the spatial domain we had a comparable description, where we essentially had the maximum repeat itself after a periodicity of lambda. In the time domain it was a t. We said that this ratio of lambda divided by t is a velocity which we call the phase velocity. In a time t, this phase point has moved from a location x to x plus a lambda over a time interval t. So, the point was the maximum phase point or any other phase point of interest was at x at time little t, and it moved to little t plus big T, the period, while making a spatial change in its location by the amount lambda. So, this was the phase velocity. However, now when we have generalized the wave as to containing frequencies being more than just the monochromatic omega naught, we do not have just one wave. What we have is a group of waves. We essentially have a wave with a frequency omega 1, there is a frequency omega 2, all of these coexist, and they also, the way I have sketched it, however small that is, however clear or unclear that is, I am wondering if I can maybe possibly zoom. zoom over this region, however clear or unclear that is. Well, these 3 waves essentially have different frequencies, but I have sketched them so as to pretend that they are somehow kept in phase. That is the other important aspect. So, if we do, then we can obviously ask this question, what about a velocity for this wave, right? We can ask this question, we are allowed to ask such a question, is not it? So, then in that relation, we are going to take a few steps to talk about these groups of waves, their velocity, and even before the velocity, we had the notion of what about the phase delay? Before velocity comes phase delay, right. So, this is again related to the fact that we had phase delay to be the propagation, the wave number k, which is the magnitude of the propagation vector multiplied by an optical path difference d between 2 waves whose whose relative phase delay is of interest to us, right. So, likewise in this case we can define a group delay, it is a new quantity of interest, group delay, contrast this with phase delay, right. So, we can in similar spirit define a group delay by once again taking the only function we know, which is what, in this case the spectral phase, and taking its derivative with respect to frequency. This gives us a quantity which has units of time, okay, and that is the phase delay. It is very straightforward for us to see that this quantity has units of time by going through the same exercise as we just did in the time frequency domain. Now, do the same in the frequency time axis. So, we had phi of omega. So, this is phi of omega at some omega naught plus d phi by d omega at omega naught multiplying delta omega plus d 2 phi by d omega 2 at omega naught multiplying delta omega square and so on, where delta omega is omega minus omega naught. Okay. So, now the left hand side term essentially has a phi, right. So, the left hand side is phase in terms of units, and delta omega has units of frequency. Therefore, whatever is multiplying this to give a phase must have units of time, agreed, because phase is frequency multiplied by time. In the time domain, it is wave number multiplied by some distance variable in the spatial domain as we had it earlier. Phi is also k times t, or phi is omega times t. Therefore, d phi by d omega is the lowest order term, okay, in the Taylor expansion, where the spectral phase is not a constant, and the first Taylor coefficient is what we are interpreting. This is the group delay. Okay. So, it's essentially a real sort of term, and just remember this very important, you can wish, misconception, that this is not the inverse of omega instantaneous. That is, what is it not? Warning, d omega instantaneous was d. Now, that is the problem. I am going to use the same symbol phi for phase, whereas group delay is d phi of omega by d omega. This is not equal to d phi, sorry, this is not equal to the inverse of d phi by dt. It inverse meaning 1 over d phi by dt. It is not. Okay. Although in earlier we did have knew the frequency is 1 over period, right, or omega, the angular frequency, is 2 pi over the time period. Okay. 2 pi is just a matter of units. Okay. Although this was true in the case of, say, actually omega naught and nu naught, this is not in general the general notion of the same thing, that if I now carry over the concept of something like this for a group of waves, it does not turn out to be reciprocal in its relationship, although the group delay and instantaneous frequency by their own right have essential physical meanings, right. So, that is really an important notion. Experimentally, the temporal phase is the following. Let us set this time axis to have a 0 here, because this definition is not unambiguous, you can shift it in. If I ask with respect to this time axis being 0 here, how does the phase vary with time? Okay. So, I can take this view that, okay, let us take this reference point. Let me set this instant of time to be t is equal to 0, right. So, how much has the phase varied as I go from 0 to, let us say, this was 3 femtoseconds, the initial this initial delta t, how much has the phase varied here? So, what is your answer? How much has the phase shifted by, phase rolled over by?
I was thinking of, so initially we had the pulse as a combination of a different frequencies. Since different frequencies propagate at different speeds in a medium.
Do not go there now. Think it is dispersionless, they are propagating in vacuum for the moment. We will come to that also, because that adds another layer of complexity to the.
That was phi of omega.
Phi of t or phi of omega is like always there. The question, if I can take the liberty of rephrasing your question, you are asking the question, in what cases is it non-trivial that phi of t is constant or phi of omega is constant, if I may interpret, because otherwise there is all this discussion is just extravagance, right. So, then just to give you another feel for this, I am still posing this question, what is the phase delay between these 2 points? What do you think is the phase delay over this delta t? How much phase has rolled over?
I would say it's a distance between two maxima.
Yeah, so how much has the phase changed?
2 pi.
So, it has changed by 2 pi. Okay. Note this delta t. Suppose I approximately mark this same delta t in the next period. Now, that is kind of here. Now, how much do you think the phase has rolled over by?
3 pi by 2.
It is a pi and 3 pi by 2 or 3 by 2 pi. So, now let us take approximately the same time difference. So, how much do you think the phase has rolled over? This is pi by 2, right? No. Is this 3 pi by 2 first of all? This was 2 pi. This is 3 pi by 2. This is here would have been 4 pi. 2 pi, 2 pi, 4 pi. This is actually 3 pi. It is not 3 pi by 2, right? It is 3 pi. So, starting from here, pi, 2 pi, 3 pi, approximately now it may be something like 3.5 pi or so. Okay, so the whole point is that now you can now say that the phase, okay, phi is a function of t. Now, had this been the ideal wave for the same interval which I would call some same delta t everywhere, the phase should have rolled over by the same delta phi. Delta phi would be the same if delta t is the same. But now it seems to depend where I start, okay, at which piece of the wave I am considering in my discussion. So, delta phi becomes a function of time. It could vary linearly, but the way we have sketched it here, this is linear in t, but it could also have been t square, t cubed and so on. It could also have been this, okay. But since you asked this question and we are sort of trying to build our intuition on things, I should bring up this notion as to what would a pulse look like if the contribution of say t to the 5 term was dominant as against the linear, right. The pulse would have looked like really very different in the sense that yeah, the frequency variation would have been kind of crazier if you wish, right. So, this pushes us to think about, if I think of a nice neat variation of amplitude and frequencies which need not even be, you know, I mean the frequency variation underneath an envelope need not be constant in time, let us say, but even with my poor sketching skills, a pulse of this nature where the electric field varies like this is different from like an what looks like some ECG signal, right. So, we can therefore subscribe to a pictorial notion of a well behaved pulse, whereas you can consider this to be a noisy pulse. But what do we actually mean by this? What we actually mean is that if I have a source and you typically I want a, I mean what is a good source? A good source is that something that produces a repeatable, predictable set of say pulses. They need not be identical, but they need to be fairly predictable in their properties. Whereas I have a source which produces say something literally like random sequence of somewhat random events in time, which could even be pulsed, which is like a light flickering or something like that, or a lightning strike, that's also pulses of light. But the point is, between the two sources you would call one well behaved and the other is kind of noisy or spiky. So, spikes are also pulses, but are we talking about ultra short accidental spikes in this course, or are we talking about ultra short repeatable optical pulses? This is the question that we have to ask ourselves. So, if I have so called well behaved ultra short pulses which are reproducible and repeatable, then in those kind of pulses the spectral profile, we are discussing all this about the amplitude profile, but there is also the all important spectral profile. Then the spectral profile would also have to be well behaved, aka predictable. So, there are two kinds of ultra short laser pulse producing sources that produce ultra short laser pulses. One is based on what we call mode locked sources, which are tabletop lasers. Or rather based on resonators, based on optical resonators. I mean that is where the power of resonators really comes to the fore. Whereas you can also have ultra short pulses from mirrorless, you can say I would call, first of all, reveal the fact that these are free electron laser sources which do not have mirrors, they are mirrorless, and they essentially do not contain the advantage of resonators, in which case you would still get you can still get ultra short laser pulses, but they will not be as well behaved as in the case of tabletop lasers. So, they can also emit pulse trains, you can make them do that by switching them on and off periodically in some sense, but the quality of pulses in this sense would be very different. So, in that it is, so what is the key difference between the two? In the case of the well behaved sources, you have in the Taylor expansion the first order term, the second order term, the third order term, the fourth order term, the fifth order term. There is a sense of convergence to the Taylor expansion of these phase, the phase function. In the other case, it is not necessarily that way. So, a spiky source versus a set of regular pulses, this is a key difference. So, if they are convergent like this, then essentially the behavior of that source is repeatable and predictable as we would have liked it to be. Okay.